Hey,
Yes.
you guys ready to bring your training game to the next level? We are talking about hiring the hazmat guys to come in and teach your classes, customized training program to fully unlock your team's potential.
When we say custom, I mean, like, seriously, everyone is completely customized. We are dealing with, actually, I just went and dropped off a pallet worth of new equipment that was just dropped off via a tractor trailer to my house, which was lovely. Neighbors loved it. But our instructors are second to none, and they are bringing a transformation to every team they touch. So get in there. So, yeah. Go to hazmatguys.com/hire us, and we'll get with you.
My bad. I thought you were going to finish that one out. You sound like you were just going to keep going.
I faded out for a second.
It's a fade. How's everybody doing on this beautiful April afternoon? Some things that we want to mention. We have the After Action Report podcast. It is going to be the first. No, it is not the first Wednesday of April 3rd.
May 1st.
It's May 1st. It's the first Wednesday of every month, May 1st. Who we have coming on in May, Bob?
Mr. Bill Hand.
The
illustrious
legend. Absolute legend in the hazmat community. Come on board. It's a long form podcast. It will not be broken up. There's video involved. Facebook, YouTube. You can comment. You can ask questions. If you want to send us some secret pictures to break his chops and ask questions, by all means, this is what it's all about. So join us.
Go check out the Battery Destroyers Club we just did on April 11th. I do have to say, the new website is up, and also the new website is up, the alternate website, and we made it even easier. So if you go to HMAF, like hazmat as
freak
F, .pro. You can see some of the alternate ideas for classes and products that we thought would be banging. As the kids said, they're hella cool. The best t-shirt designs that are absolutely funny. You got to check it out. Classes, I mean, like products, the absolutely ridiculous products, like a pencil case. Ridiculous.
I love the pencil case. This is not a good example of the shirts because these were prototypes and they definitely faded a little bit. But what do we got? That's the bird cage, right? So it's a bird in a bird cage. The bird's dead on the bottom and it says the original meter. It's a phenomenal design. Old school meter. That's right.
So a lot of conferences. We just finished up with OMRA, Michigan. We got Cold Zone coming up, Oklahoma, South Carolina, Baltimore, and we are going to now Virginia. That is kind of in the hopper right now. So I think that's all for right now. So
Anyway, to the topic of today's conversation. Today's conversation is words matter. And this is a topic that we really wanted to hit on because through our years in the fire department, a lot of mean things have been said to us.
Yes.
And our feelings have really, really been hurt. So we want to really kind of understand and let everybody feel like this is a safe place to talk about how words matter in our interaction.
All right, I'm going to stop you right there. That is absolutely not where we're going on this.
Wait, what the hell else could words matter possibly be?
Okay, this is a long... I think they're going to like this one. Is that there are words, concepts, or constructs that are they're conflated a lot because there's a parallel. Either the word is like similar or the concept is constructed semi-similar. So we are going to do many of these things, but luckily they are not going to be done in sequential order. We're going to throw them in whenever we feel like them. So I'm thinking we're probably going to get through 2 different topics or concepts per episode, and we'll just leave them there. And I have a list of like 30.
So I do want to say, if you've ever been in a class with me where we're talking about chemical physical properties or doing classes, I have a term for what we're about to do, and it's called technical douchebaggery. Right. So I always turn around and I go, you always know who the technical douchebag is in the group when they turn around and go, actually, that's not the right use of the word. If you take this information and you do that, you are a technical douchebag and we will hate you. The reason that we're giving this information out is because we speak in generalizations, right? When now me and Bob both have chemistry backgrounds. We both have physics backgrounds. So we can understand a few layers deeper than what the normal technician on the field needs to know. And I can promise you that when we're describing general concepts to you, we are lying to you. It is almost all bullshit. Not from the point of view of the information and how it applies to your response. But if you were to tell if you were to take one of our classes and then go to a chemist and be like, I heard that the electrons orbit around, they'd be like, no, that's not how it actually works. So be very careful with these words. They matter when the situation dictates, and it allows you to really parse out fine details in situations where things may not really make that much sense.
So this first one, though it might sound simple, is surprisingly more complex than you would think, because people think it is as simple as just saying, oh, organic means carbon and hydrogen. And I will say, for the most part, yes. For the technician on the street, yes. But we're going to go a little bit deep. And some things we, maybe you don't give a shit about, but it's all about opening up your eyes to other things. So,
okay. So then what is organic chemistry?
Well, the first thing is it focuses on carbon. It's a genre of chemistry, right? So there's people that get PhDs in organic chemistry. There's people that get PhDs in inorganic chemistry, redox chemistry, whatever it is. So organic chemistry is like primarily concerned with compounds that contain carbon. It's the chemistry of life, basically. It's almost all molecules in living organisms are based upon these carbon skeletons.
Yeah. So not that we like organic chemistry, right? Nobody actually likes organic chemistry. I'll put that out there right now. It's one of the most hated classes in chemistry is organic chemistry, but it is hated because it is so complex, right? Organic materials, they can change from like one simple carbon, 4 hydrogens to these vastly complex structures with chains and rings and branch networks. And it's this versatility that gives it, for lack of better words, life, right? It's this versatility that allows life to operate and form and function. And, we are concerned about organic chemistry because we are organic chemistry in motion. And if we take an organic compound and we put it into our body, that tends to lead to some form of toxicity, whether it's acute or chronic.
Now, some common examples would be sugars, proteins, DNA. Right. All these are example of organic compounds, or even substances that are not maybe living, but plastics, gasoline, medications are also organic chemicals.
Yeah. So the nasty chemical sprays on the plants that people want to stay away from when they try to eat organic, this is not what organic is talking about, right? Because those chemicals are actually as organic as it gets.
Yes.
All right. So I'm not going to say it's the opposite of, but it is kind of an inverted study is inorganic chemistry. Inorganic chemistry deals with all the elements in the periodic table as well as their compounds, except for those containing carbon and hydrogen, which would be the organic chemistry. Things like this could include the study of metals, the study of minerals, your salts, literally anything else that doesn't contain carbon and hydrogen is going to land in the inorganic chemistry realm.
Right. It's a huge, broad, range of substances that aren't organic. So basically, if it doesn't have that carbon hydrogen bond, it's inorganic, and it's going into that whole genre over there.
Right. Now, because of the way carbon has 4 electrons in its valence shell and it wants to do the octet rule, it can bond up with 4 individuals and the bond angles and all this other stuff. Carbon is phenomenal at forming large compounds, which is what we talked about in organic chemistry. In organic chemistry, they tend to be a lot less complex, although there are exceptions to that generalization, right? The complexity in inorganic chemistry tends to be not milder, but less probable.
Yeah, that's why a lot of people like it more, because it's a little bit less complex. Yeah.
You deal with the stereochemistry of an isomer of some long chain molecule with multiple benzene rings and nitrile groups, and you're like, fuck this.
So this is going to have things like catalysts and material sciences like semiconductors or ceramics, and it also includes the study of fertilizers, metals, and glasses.
Yeah. So what are some of the differences between inorganic chemistry and organic chemistry, right? Because that's what we're doing in this. We're trying to parse out what these differences are. Organic chemistry involves carbon and hydrogen, which we talked about, but that's the building block of organic chemistry, right? Organic chemistry also has the ability to bring in other elements on the periodic table, like oxygen, nitrogen, sulfur, phosphorus, but it also has the ability to bring in like complex chemistry or complex inorganic chemistry that then attaches itself to the organic chemistry, making it something that's a little bit more happy.
That is true. Now, the complexity and the bonding of this stuff is that the organic compounds often have complex molecular structures with covalent bonding. Inorganic compounds may have bonding types such as ionic, covalent, metallic. They can have all types of different stuff and have probably simpler base structures.
So I was teaching a chemistry week class this week. I won't tell you where because I don't want anyone to get in trouble, but you know where if you're hearing what I'm saying. And we're talking about sp2 and sp3 bonds, right? Ooh. To a bunch of recruit hazmat people. The greatest question in the world came up and they said, how would we use this information in the field? And my answer was, you won't.
You won't. Let's take a break.
And then they said, then why are you teaching this to us? And I said, because this state requires it. Silliness. All right. If there is an organic chemistry out there, we're talking about how important organic chemistry is to us. We want to know how to be able to detect organic compounds, right? So, you should understand that organic chemistry exists, and you should understand how to go to your toolbox and pick up specific tools to be able to identify this incredibly important chunk of chemistry that is vitally important to us.
Now, I'm going to say, before we even start this thing, the vast majority of you do not have this technology on your rig. Like, I don't think anybody anywhere has this on the rig, but I want to, like, again, we're going to give you this, hey, this is a thing that's in a lab, and you might hear some nerds talking about it. So this one kind of is something you might have heard of, spectroscopy methods, right? We call organic methods are typically analyzed using spectroscopy methods such as infrared spectroscopy or nuclear magnetic resonance, or NMR. This is kind of a common thing. IR spectroscopy detects the molecular vibrations that are characteristic of certain functional groups, and NMR spectroscopy is extremely useful for figuring out the structure of organic molecules by observing the magnetic properties of the nuclei like hydrogen and carbon.
A lot of good stuff. And we actually do see and with more and more popularity, people grabbing the IR spectroscopies, but I have yet to see a nuclear magnetic resonance machine, floating around somebody's rig. But I'm sure one day it will exist. So the technology is constantly improving and getting smaller. All right, chromatography. Techniques like gas chromatography and high-performance liquid chromatography are prevalent for separating and analyzing organic compounds. These methods are highly sensitive to organic molecules, allowing the detection and quantification of very, very, very low concentrations of organic substances.
Another one you probably have heard of and you may actually have is mass spectroscopy. Right, and this is often coupled with chromatographic techniques. Mass spectrometry provides detailed information about molecular mass and the structure of organic compounds, which we knew, but this is crucial for identifying unknown compounds and confirming the purity of a substance.
So this is like the MS. This would be the MS of the GCMS.
Yep.
Which again is a technology that is out there, but is not rare. But there is a possibility that you have access to it, even though your team might. And this is where you have to start to understand what resources are available to you. A lot of areas are supported by what's known as a CST, which is your civil support team. It is a state type of an entity, and they absolutely 100% will carry GCMS and possibly some of the other ones that we have talked about with the people on there who are experts in how to use them. So if you don't have some of these resources in your actual department, you really should learn how to gain access to them.
Love it.
So then how do we detect inorganic compounds, right? Inorganic compounds can be detected by things like an atomic absorption spectroscopy. This method is highly effective for detecting and quantifying metals and metalloids in the sample. It measures the concentration of a gas phase atom by absorbing ultraviolet or visible light and I can't pronounce this word. Emitting electromagnetic radiation. So, we start to look into the field of non-organics. Some of our other ones that we mentioned can pick them up, and it kind of depends on the size of the molecule and the bonds and things like that. But these would be specific for things like salts, metals, things that the IR could not pick up.
Another technology you definitely do not have on your rig is called inductively coupled plasma, or ICP. Now, techniques like this, they're an optical emission spectroscopy and ICP mass spectroscopy used to analyze inorganic compounds, especially metals, in environmental samples, foods, and materials. These methods are known for their ability to handle complex matrices and provide rapid multi-elemental analysis. So
this whole time I thought it stood for Insane Clown Posse.
No.
I'm so disappointed. Another technique would be X-ray fluorescence, or XRF. It is used for the elemental analysis of inorganic compounds, particularly for those that are kind of in more of a solid form. It's a non-destructive method, which is always nice because if you're not destroying it, then you're not converting it to something else. And it can quantify elements from magnesium to uranium. Now, it's not qualifying, it's quantifying. So it's literally telling you how much of that substance is going to be in this sample. And it is an absolutely invaluable tool used in material science and industrial applications.
Now let's get into the 4 different technologies we know you have. I looked on your rig and I've been inside your. I'm in your closet now.
If you're going to argue that fact, then we're going to come and prove you wrong.
Yes. So electrochemical sensors. The principle behind this is that they detect gases by measuring the electric current that results from a chemical reaction, which coincidentally enough is called a redox reaction, at the electrical surface where the target gas is present. And how they use them is that they are widely used for detecting gases like carbon monoxide, hydrogen sulfide, and oxygen levels. The electrochemical sensors are effective for both organic and inorganic gases, depending on the specific sensor design and the target gas that we want.
Okay, another one that's really good for organic material, but you can use it to pick up inorganic material. And here's that's part of the learning and understanding these meters. We talk about this really heavily in the modular metering class, where we dive into the language of the meter and we dive into what the meter is telling you, is understanding what it does and doesn't pick up and how well it picks everything up, because all of it makes a difference in your operation. So catalytic bead sensor is great for flammable materials, which I would say Well, I guess statistically speaking, 60% of everything transported is going to be a flammable material, and many flammable materials are going to be in the organic range. So you can get a pretty good bet to say that if you're picking up something flammable, it's going to be an organic. These sensors are going to measure the gas through the oxidation of the gas on an active catalytic element. Basically, this element heats up due to an oxidation reaction, gives off heat, heats up the bead. The bead then changes its resistance. That change in resistance is picked up over voltage, and that change in voltage then tells you how close you are to the lower explosive limit. It is primarily used to detect, again, combustible hydrocarbons, which makes them really useful for picking up organic compounds, especially the ones that pose fire hazards. If it is an organic material and it doesn't burn, it's not going to pick up on your catalytic bead sensor. So catalytic bead, knowing what it's good for, knowing what it's not, I would not take my catalytic bead sensor to detect most halogenated hydrocarbons, which turn out to not have any kind of flammability, and it's not going to pick it up in any way, shape, or form.
Another technology we've talked about before and is NDIR, non-dispersive infrared, and these work by absorbing specific wavelengths of infrared light as it passes through a sample, and the absorption is measured by determining the concentration of certain gases. We use this for measuring carbon dioxide, which is inorganic, and various hydrocarbons and other organic vapors. And it's particularly effective on gases that have a strong infrared absorption characteristics. So,
yeah, I hope that as time goes on, our repertoire of NDIR sensors increases, because it's such a great technology. It has so many more advantages over electrochemical sensor. If you have the option to start transferring things over to NDIR, I highly recommend it. I like it a lot better than electrochemical, but that's for another day. Colorimetric detection, right? Something that is often overlooked this day and age, whether it's colorimetric detection of tubes and papers or colorimetric detection during something like a HAZCATting, it is unfortunately going by the wayside, and we are going to try to push this and bring it back to the forefront, because it has really unique properties to it. These devices change color in response to the presence of a specific chemical. Now, this is a little different than most of our other meters, minus the NDIR, our primary meters, that pick up generalizations, okay? Even my electrochemical sensor, my CO, even though it says CO, it can pick up a wide range of materials. Our colorimetrics really narrow down that range. So you end up getting a color change as a result of these chemical reactions between some kind of target substance and some kind of reactive agent on either the paper or the tube. They are extremely versatile. They can pick up a huge range of specific substances, from chlorine, which is an inorganic, to ammonia, which is also an inorganic, and flammable. So there's one your CAD bead will pick up that's an inorganic. And it's going to pick up a whole bunch of organic solvents as well. I like them because they can be area dependent. What do I mean by that? You take and you do an analysis of your team and your hazards floating around, and you can develop a library of these colorimetric tubes that are specific for large quantities of product that may be in your first due area that you may not be able to get, say, an electrochemical sensor for. They are highly appreciated for their simplicity and how easy they are to use.
Okay, I'm going to try to pack in this next conflation point, or at least wording point, the definitions point, in the remaining time we have here. It is 5 different terms that we use for basically changing phases, sorry. Mm-hmm. And one that is a little bit different, but not the same. So the first one is evaporation. When I elucidate,
elucidate. That's an SAT word right there.
That was good. I just popped that out of my head.
We're going to pause so that you have the opportunity to look that one up.
This is a process where the molecules at the surface of a liquid get enough energy to enter the gas phase, right? So this is a liquid to vapor type operation, right? This is an evaporation can occur at any temperature. does not need to require the liquid to reach its boiling point. It's typically a very slower and quieter process than boiling. And so that's important because long duration liquid to vapor is called evaporation.
Right. But if I were to take and do this all at once where I heat up where I heat up the entire liquid, I go from taking gas molecules that are at the surface, which was kind of the key word to evaporation that Bob said, was it's at the surface, right? I take that and now I start converting everything under the surface to gas. Yep. This is the classic boiling that we see when we're going to cook our pasta, right? We're looking over it and we're watching the bubbles form at the bottom of the boiling water. And when it comes to a full boil, guys, that's not air. It's not bubbling air. It's literally the gas. It's gas water, right? Which is why it's steam, and it's coming from the bottom. It's coming from within. It's coming from everywhere. So boiling occurs when a liquid reaches its boiling point. In order to do this, I have to have enough thermal energy to make all these molecules want to try to escape at once. It's characterized by a rapid formation of the bubbles, like we talked about at the bottom of the pan. And that is one of the key differences, is the bubbling. Now, just like when we're watching the pot boil, not just a few bubbles can mean that it's boiling. As the temperature goes towards the boiling point, you're going to have an increased rapid boiling. So if you ever wanted to turn around and be like, how long would it take for something to boil off at its boiling point? You can refer to a pot of water on the stove as a pretty good reference for how long it would take that amount of water to evaporate at a full boil.
Okay. The word is vaporization. And what this one, so evaporation is temperature independent. Mike's is temperature dependent. Vaporization is we artificially put a gas into a liquid format, and now it's going to do a phase change from liquid to gas. This can include both boiling and evaporation, depending on the conditions. So this happens usually really quickly. When we vaporize, it's like poof, it's gone.
Yeah. And the term vaporization, because it includes both boiling and evaporation, we can tie in some of the physics that happens during vaporization as well as condensation. And that has to do more with the heat of vaporization and energies that are both taken from the environment and given to the environment whenever you vaporize or perform a condensation. And that condensation is the opposite process of vaporization. Although it's not a term for necessarily transferring from a liquid to a gas, condensation really is the reverse process where a gas transforms into a liquid. It's relevant when we're discussing the full cycle of phase changes, and we most often have it occur when we're talking about weather and dew point in the morning. That's generally when we talk about condensation. Our process and concern is usually more about vaporization than it is about condensation.
I think I might have wrote the wrong word where I put gas transforms to a liquid. I think it's more of a vapor transforms into liquid.
Well, you can have.
I think I made a mistake.
You can have both, right? Because if you have
chlorine.
You have chlorine gas. When that gets cold enough, it condenses inside. So although we do generally think of it as a vapor, right? We think about it as water vapor. Really, what is the difference then? And I don't know if this is part of the show, and if I'm giving it away for future, I apologize. But what is the difference between vapor and gas?
Right. One comes from a liquid, and one is definitively by vapor pressure.
Right.
Gas.
So you can have both performing a condensation.
Everybody, all the kids love to say this one, sublimation, and it's opposite twin. Just dropped out of my head. What's the opposite of sublimation?
Oh, it's on the. I just did this.
It's right on the tip of my tongue.
It starts with a D, right?
Deposition. So this is a different phase change. This term describes the direct transition from a solid to a gas, skipping the liquid phase completely. under specific conditions. So while not a liquid to gas transition, it is often discussed in the context of phase changes. So the deposition is going from a gas straight to a solid.
The next and last term for today is going to be distillation. And this is really an application-based process. What this does is we heat up a liquid with a mixture. And as each one of the chemicals, well, how should I say this? As each boiling point reaches the boiling point of a specific chemical in that liquid, we get a leveling off of the temperature change, and we get an evaporation of that specific chemical. So this is definitely an application process used to help separate different chemicals of different molecular weights.
Right. So when they say, "Oh, we're distilling it," what they're basically saying is they're removing impurities in order to increase the concentration of a higher boiling point substance. It's used a lot in industry,
and it's the
first, my basement,
and it's in your basement, and it's the first step in the GCMS.